Boys and girls, let's take a look at the second part of our Unit 2 study guide. Tonight we'll be focusing on identifying the different number types that we have in the real number system, as well as being able to order and compare these numbers. Let's turn to the second page, front and back. Well, boys and girls, let's take a look at part 2 of our study guide. And before we even begin this, I want to apologize. If you go to go to the very back page, the back side of the back page, numbers 55, 56, and 57, they're bad problems, okay? There is not a correct answer in the options for answers. So I'm sorry about that. 55, 56, and 57, they're bad. I'm going to have to go back and edit the study guide for next year, but I'm sorry about that. Those are all bad problems. The rest are good, though. The rest are good. Okay, well, let's take a look at the second page, front side. It asks us to identify which type of numbers each group of numbers belong. Okay, so we have now groups of numbers. We're not just focusing on one number. And what we want to do is we want to take a look at -3, 2, 0, -14, and 101, and kind of go through our checklist and ask ourselves, do all of these numbers belong in any particular number family? And we'll start off with natural. Now right away I can say, I know natural numbers are all just regular counting numbers, 1, 2, 3, 4, 5, all the way up to infinity. They're just regular counting numbers. And right here, -3 disqualifies. It can't be, this group cannot belong to natural numbers. Then move on to whole numbers. Whole numbers would include all the natural numbers plus 0. So we could use 0, but then again we have -3 and -4. So what do we do with that? It disqualifies it. This group would not belong to the whole number family. And then I move on to integers. I know that integers would be all whole numbers and natural numbers and their opposites or negatives. And sure enough, okay, we've got 0, we've got natural numbers and whole numbers, and we have negatives. So these numbers would be considered integers. Okay, they're all integers. And we could also say that they're rational numbers as well, but we're not going to worry about that right now. Let's go through, I think if you go 3 groups down, you'll come to pi, square root of 2, negative square root of 19, and then also square root of 7. And we can say, no, they're not natural numbers, not even close. They're not whole numbers. Although there's a negative, it doesn't make them integers. These would all be rational numbers. And what defines a rational number, now rational numbers do include these other subsets of natural, whole, and integers, but what would make this exclusively rational numbers is the fact that these are all decimals that are non-repeating and non-terminating. Okay, they have no end and there is no pattern. Pi, we don't know what pi is. We know it's approximately 3.14, but those decimal the digits after the decimal point just keep on going, and there's no known pattern or order to that. And the same thing is true with these other guys. But just on pi alone, that would disqualify it. So we would have to say that these numbers, this number group here, would fall into the rational number family. Whoops, I didn't spell rational wrong. Let me spell rational correct. Okay, so rational. There we go. Rational. Let's look at the next section. Now we're comparing numbers. Let's jump to number 43. We did a couple of these problems in class. I think we did 40 through 42 in class. Let's jump down to 43. We are comparing 5/10 to 1/5. Well, they both have 5s in them, but that doesn't make them equal. I know 5/10 is exactly that, 5/10. 1/5. Let's, I have a pretty strong feeling I think I know the answer, but let's just prove my answer. I'm pretty sure that 5/10 is greater than 1/5. Let's see if I'm right. 1/5 is really 1 divided by 5. 5 will not go into 1, but it will go into 10 2 times, and I'm done. So my answer is 2/10. Okay, and yes, 5/10 is greater than 2/10. So when we're comparing numbers, we have to kind of get them to be the same number type if we want to be sure. And I like switching them both to decimals. It makes life easier. Okay, this looks pretty scary and complicated. Here we have a fraction with a radical in the denominator, and we're comparing it to a percent. Well, what do I do with that? Well, I know that 75% is 75 out of 100, right? It's 75 hundredths. Now, I'm going to do a little work on this one. Let's see if we can simplify this. 1 plus 2 is 3, so that's my numerator. And the square root of 16 is 4. Okay, so the square root of 16 is 4. 1 plus 2 is 3. So I get 3/4. And I think we already know the answer, but let's just prove it. 3/4 is the same thing as 3 divided by 4. Okay, 4 will not go into 3, but it will go into 30 7 times, which is 28. I subtract, I get 2. I bring a 0 down. 4 goes into 25 times. I have 75 hundredths. Hey, these guys are equal. And I think you get the idea of how to handle that. Okay, boys and girls, let's hop down to number 50. Now we are ordering these somewhat strange numbers. Not the normal numbers we would think of putting on a number line, but we can do it nonetheless. Our first number is pi. Now I know that pi is approximately 3.14, and 3.14 would be between 2 and 4. And it's going to be a little closer to, 4 than 2, so I got 3.14, be right there. Check, got that one. I know that the square root of 18, you might say, how do I do that? Well, let's estimate. I know that the square root of 18 is between the square root of 16 and the square root of 25. The square root of 16 is 4, the square root of 25 is 5, so it is somewhere between 4 and 5, which would put it, well, here would be, 5 would be right about there. So it would be somewhere between 4 and 5. It would be over here. So I can say that the square root of 18 would be right about there. Check, got that one. Then I have the negative square root of 40, and I'm going to just focus on the negatives means I kind of have to switch the order. So it would be between the square root of the negative of 36 and the negative of square root of 49. Okay, the square root of 36 would be negative 6. Square root of 49 negative would be 7. So it is somewhere between negative 7 and negative 6. So it's going to be right about there. That's going to be where I'll find the negative of the square root of 40. Check. Okay. Negative 7 and 35 hundredths. Okay. That makes it easy. It's going to be between negative 6 and negative 8, but a little closer to negative 8. So I can put negative 7 35 hundredths. And then finally I have 75 hundredths. Just to make life easier, I know that 75 hundredths is going to be, if 1 is right there, 75 hundredths would be right about there. And I'm done. I think you get the idea. Well, our last section that we're going to take a look at is simplifying these square roots. Okay, we're going to look at 61 and 63. And when we simplify, the first step is just find the prime factorization. Let's add a little color. We're going to find the prime factorization of each of these numbers. I know that 108 is going to be 2 times 54. There's 1 prime. I know that 54 is 2 times 27. And I know that 27 is 3 times 9. And 9 is 3 times 3. Okay, so I take all of this and I put it, the second step then, is to put the prime factorization under the radical, and then I look for perfect squares. And the way I find perfect squares, I look for repeats. Like here I have 2 times 2. And 2 times 2 is 4. That's a perfect square. And then I have 3 times 3. That's another perfect square. That's 9. And then I can factor these out. Okay, the square root of 2, the square root of 4 is 2, and the square root of 9 is 3. So that's 2 times 3, and what I'm left with inside the radical is the square root of 3. So then the last step is just clean it up. 2 times 3 is 6, so 6 times the square root of 3 is the square root of 8 in simplest form. Let's do the same thing with 75. Now, no, 75. I'm going to think money right away. 75 cents. That's 3 times 25. Okay, and 5 is 5 times 5, and I'm all primed out. So this would be, I'm going to go over here, this would be equal to the square root of 3 times 5 times 5. So the prime factorization inside the radical. And I do see a perfect square. I see a repeat there. 5 times 5 is 25. So the square root of 25 is 5, and I'm left with 3 on the inside. So there's my 2 answers. 5 times the square root of 3 is the same thing as the square root of 75, and 6 times the square root of 3 is the same thing as the square root of 108. As always, I hope that was helpful, and I'm looking forward to seeing you tomorrow. Please bring your questions. Oh, never mind. I have questions for you. It's called a test. See you tomorrow.